While solving Cauchy problem for quasi-linear equations, one of the steps was to pass characteristic curves through points of the datum curve. For that, what we do is we solve a system of characteristic ODE with initial condition, so that the point initial condition point lies on the datum curve. Now, when it comes to the general nonlinear equations, if you want to do the same thing, we did not have a complete system for the characteristic ODE because it involved P and Q which were unknown. Therefore, we extended the system to a system of characteristic strip, system of differential equations for a characteristic strip. Now, we would like to solve this, but now the problem is that characteristic strip is not known on the datum curve. On the datum curve only the values or the initial conditions for x, y, z will be known. Therefore, we need to derive initial strip. That is what we are going to do in this lecture. We start with a recap of what we have done so far in the characteristic method for general nonlinear equations, and then we find the initial strip, and then we take the third step, which is to define a candidate solution, and first steps in the step 3. In the next lecture, we are going to conclude the entire all the 4 steps. So, this is to just make you recall the notation. QL stands for quasi-linear equations, AUX plus BUY equal to C. GE, we call it general nonlinear equations, sometimes people call fully nonlinear equations. It is f of xyu ux uy equal to 0. Now, in the solution of the Cauchy problem for general nonlinear equations, where are we? Let us look at that. Recall the key steps involving in the solution of Cauchy problem that we proposed for general nonlinear equation. Step 1 is obtaining a system of ordinary differential equations for characteristic strip, which we have done. Step 2 is finding an initial strip, we are going to do today, and step 3 defining a candidate solution and establishing that the candidate solution is indeed a solution to the Cauchy problem will be taken up in the next lecture. So, step 1 was successfully implemented so far. Let us recall the difficulties which are new to GE when compared to QL, and what were the ideas that helped us to overcome them. Difficulties and their resolution in step 1. Our analysis was motivated by the quasi-linear equations. Quasi-linear equation QL gave us a characteristic direction. Characteristic direction gave rise to characteristic curves. Characteristic curves made up an integral surface. The difficulty 1 for general nonlinear equation is the equation does not give away a characteristic direction. A useful idea was we observed that for quasi-linear equations the characteristic direction is the envelope of possible tangent planes. Actually, the envelope of possible tangent planes is a straight line whose direction is a characteristic direction. So, we found that the same idea works for GE as well. A characteristic direction at a point P x y z is given by Fp, Fq, P of P plus Q of Q. The Fp of Q denote partial derivatives of f with respect to the variable P and Q respectively, and this small pq satisfy f of x y z pq equal to 0. Capital P actually is standing for x y z. Now, what is the difficulty number 2? Characteristic ODE system is incomplete for GE because we were looking at finding a curve having characteristic direction, which was given by this dx by dt dy by dt dz by dt equal to Fp Fq P of P plus Q of Q. We were looking at solutions to this whose image will be a curve, okay, and with this condition x0 equal to x0, y0 equal to y0, z0 equal to z0. Then this will be a characteristic curve passing through the point x0, y0, z0, Unfortunately, in this system PQ are involved and PQ also depend on the location where you are on the characteristic curve that you are trying to find. So, P and Q are dependent on xt, yt, zt. That is why Cara ODE, that is this system is called Cara ODE, it is not solvable. So, we need to complete this system, that is what we did. We derived a system of ODEs for the characteristic strip, which is a system of 5 equations. Now, we need to find a solution to this. What is the next step? As I told you at the beginning of this lecture, is to find solutions to this, so that x0, y0, z0 is a point on the datum curve, let us say Fs, Gs, Hs. But what will be the initial conditions for P and Q? Those are not there. So, we need to derive that. That is what is called finding an initial strip. Okay, initial curve, that is a datum curve, is known Fs, Gs, Hs. As S varies in the interval I, we are going throughout the curve gamma. Now, we need to find Ps and Qs, and Ps and Qs are not arbitrary functions. They should be such that Ps Qs minus 1 should be the normal to a possible tangent plane that we want to find. So, it is something tied with the equation, the Ps Qs. Okay. For this step, we are going to assume that the initial data is C2, F, G, H are all C2 functions. This is only a temporary requirement. We will see a comment later on saying that okay, this is not needed at some point. As I told you, to derive the equations, we can assume anything that we want, but having got the equations, we have to try to show that things work with the minimal assumptions. Assuming FGH is C1 is somewhat reasonable, C2 is too much, it is not that much reasonable, but this we are going to do only to derive this an initial strip. Okay. We will see that. We will also see where are we going to need this C2s. So, finding an initial strip. So, step 2 in solving Cauchy problem is to find an initial value problem for Cara strip ODE. The datum curve gives rise to the initial conditions for x, y, z. We need to find initial conditions for P and Q. In other words, we need to extend the datum curve to an initial strip. The support of the strip will be the datum curve. So, finding an initial strip, how do we do that? So, let zeta t be xt, yt, zt, pt, qt be a solution to Cara strip ODE. So, it follows from Cara strip ODE that along a characteristic strip d by dt of this is 0. How does it follow? You do the chain rule. So, it will be fx into x dash t plus fy into y dash t, fz into z dash t, fp into p dash t plus fq into q dash t, and if you use these equations, it turns out that you end up with 0. Therefore, d by dt of f of x t y t z t p t q t is 0. So, that means this function t going to f of zeta t is a constant function, because its derivative is 0, it has to be constant. If it is constant, it will be equal to f of zeta of t naught for any t naught, but I will choose t equal to 0, because t equal to 0 is where I am going to stay on the datum curve, at least x0, y0, z0 will be on the datum curve. Therefore, we are going to require that f of zeta 0 is 0, that is what we are going to ask. So, if we choose an initial strip zeta 0, which is x 0, y 0, z 0, p 0, q 0, such that f of that is 0, it means f of zeta t will be 0 for all t in J. So, recall that the Cauchy data is given by x equal to fs, y equal to gs, z equal to hs. We are interested in passing a characteristic curve through every point of gamma. Since Cara strip ODE is a coupled system involving P and Q also apart from x, y, z, which only matters to find a characteristic curve. To find a characteristic curve, you need xt, yt, zt, but the equations involve P and Q. So, we first have to determine an initial strip having the datum curve as its support. In other words, at every point of the datum curve, if this is gamma any point, we need to associate a vector. I am saying vector because two numbers are there and this should be having this finally this property that this is P S, the point is S, okay. This is F S G S H S. Okay, the strip is FSGSHS PSQS, the support is FSGSHS. Since the integral surface must contain a part of gamma on it, we should have Hs equal to U of FSGS. It should hold for S belonging to a subinterval of I. Now, once you have that, differentiate this equation with respect to S. You get H dash S equal to Ux into F dash plus Uy into G dash by chain rule. Since Ps equal to P is supposed to be Ux, right, Q is supposed to be Uy, that should also hold. So, we demand this Ps equal to this should happen, Qx equal to this should happen. Therefore, what does this imply? The equation that we obtained in the previous slide, H prime equal to Ux F prime, Uy G prime. Now, Ux Fs Gs must be P and Uy must be Q. Therefore, we need to solve for Ps and Qs in terms of S coming from this equation capital F of Fs Gs Hs comma Pq equal to 0 and P F dash S plus Q G dash S equal to H dash S. So, phi b is this equation and this is the equation of the partial differential equation. Okay. The role P and Q are actually for Ux and Uy. So, that is why we demand these two conditions. So, now if you notice this is a function of Fs Gs Hs are given, okay. Therefore, F dash is known, G dash is known, H dash is known. So, what it involves is P and Q and a function of S, something S. Okay. So, you can think of this as a function of S P Q equal to 0, another function of S P Q equal to 0 and you want to solve P Q in terms of S. So, implicit function theorem says that if we know a special solution for some S equal to S naught, okay, P naught Q naught which satisfies this as well as this. That means capital F of S naught comma G of S naught comma H of S naught comma P naught Q naught equal to 0 and P naught F dash S naught plus Q naught G dash S naught equal to H dash of S naught. If such P naught Q naught are given and a certain Jacobian condition is satisfied, non-zeroness of certain Jacobian, we will do the details on the next slides. Then there will exist functions, you can express PQ in terms of S, essentially that is what we want. So, there exist functions S going to Ps, S going to Qx, of course the conclusions are local, therefore these functions will be defined on an interval containing S0 where this Jacobian condition is satisfied and where a particular solution P naught Q naught has been found, such that these functions are differentiable and they are solutions to the above system. Moreover, they are unique with respect to the above properties. Implicit function theorem when applicable it gives you unique solution. So, when S equal to S naught P Q equal to P naught Q naught, if that is a solution to the system of equations, that is exactly this which I have read out earlier. Okay. So, in order to put our problem in the setup of implicit function theorem, we define two functions phi 1 and phi 2. As I told you P 1 of S comma P Q, because Fs Gs Hs are known, it is simply a function of S. That is why S, P Q are unknown quantities. I want to solve P Q in terms of S. So, I have 3 variables here. So, S varies in the interval I, P Q vary in the interval R cross R I have put, but it should be that wherever capital F is defined for this P Q, right. So, it will be the projection to the last 2 coordinates P Q of the domain of omega 5, that is where it makes sense. So, if you assume that that is omega 5 is such that the last two components are, then is r cross r, otherwise it is going to be the corresponding projections to the last two coordinates that will come in place of r cross r. Because f should be meaningful after all, right. Here I am defining this function for p and q belonging to r and r. Of course, that makes sense only if f is defined for those p and q's. So, set of all p q for which f is defined, I will consider this function. So, in that case I will not write r cross r, I will write something else. Okay. So, with this correction, phi 2 of s p q is the second equation that we had on the previous slide. We are interested in its solution. What is given is S naught P naught Q naught is a solution. You have to find the P naught Q naught such that S naught P naught Q naught is a solution. So, that is what we assumed. Now, to apply implicit function theorem, we need to check that functions are C1 functions, phi 1 phi 2 are C1 functions, are they? Yeah, with respect to S, if f g h are C1, fine, this is C1 and capital F itself is C1, therefore, composition will give C1. P q are appearing in this and we already assumed F is C1 with respect to all the components, therefore, P q also it will be C1. So, phi 1 will be C1, no problem. Phi 2, C1ness of phi 2 will involve C2ness of F. So, this is where we need FGH to be C2. Okay. In terms of P and Q it is linear, so it is all is C infinity. So, phi 2 is C1 provided we assume the initial data, that is datum curve FGH are C2 functions. This is where we need FGH to be C2. Okay, fine. Now, the Jacobian of phi 1 phi 2 with respect to P q at the solution that we already found S naught P naught Q naught of this system, that should be non-zero, which is this dou phi 1 phi 2 by dou P q is simply the Jacobian which is here, dou phi 1 by dou P, dou phi 1 by dou Q, dou phi 2 by dou P, dou phi 2 dou Q will come. Now, at the point S naught P naught Q naught, that you can compute from the expressions of phi 1 phi 2, it will turn out to be f p at zeta naught, f q at zeta naught, f prime s naught, g prime s naught. Zeta naught is this 5 tuple, f s naught, g s naught, h s naught, p naught, q naught. This is non-zero. We have to assume that. Assume the above condition on Jacobian. Okay, done. Now, we can apply implicit function theorem. It gives us unique functions p equal to ps and q equal to qs, which are C1 on an interval containing s equal to s naught. Let us still denote it by I for convenience. If you want, you can make it I dash, does not make any difference. And what is the property? Ps and Qs solve the system phi 1 and phi 2. Phi 1 S Ps equal to S Ps Qs equal to 0, phi 2 of S Ps Qs equal to 0, and at S equal to S naught it coincides with P naught, Q coincides with Q naught. Thus, an initial strip has been determined. So, this completes successful implementation of step 2 of our program. So, initial strip consists of the datum curve gamma which is given to us, and along with planes, planes essentially means the normals to the planes Ps Qs minus 1 attached at each of the points of gamma. Okay. What we have shown is that if the Jacobian condition is met at an s equal to s naught in a piece nearby, that is some part of gamma, there we can do this. That is what the implicit function theorem said. In any case, our theorem is going to be local. We are always going to fix some point and going to assert that near this point P0 on the datum curve gamma, there is an integral surface which contains a piece of gamma. Therefore, this is absolutely fine, and initial strips have the datum curve as the support, okay, if you can find throughout all the points. Okay, now let us go to the step 3, which is defining a candidate solution. To define a candidate solution, first thing is we have to solve characteristic strip equation with the initial strip that we have got. So, here we assume that f is C2, and so let this represent solutions to characteristic strip ODE satisfying the initial conditions. For x, y, z it is f, s, g, s, h, s. For p and q it is small p and small q of functions of s, which we have determined in step 2, that is the initial strip. That means if you look at the trajectory of the solutions, the first 3 coordinates at t equal to 0 pass through the point f, s, g, s, h, s on the datum curve, and remaining 2 are supposed to be giving you the components of the normal at that point. That is why the strip. Now, existence of solutions like this follows from Cauchy-Lipschitz-Picard theorem. That is why I assumed f is C2, because the right hand side will involve Fp, Fq, etc., right. So, to guarantee that right hand side is Lipschitz, one easy way to do is assume that right hand side is C1, then it will be locally Lipschitz, and then we have existence of unique solutions. So, that would require f is C2, that is why I have added f is C2. So, solutions are unique because of that. Otherwise, you have existence, continuity is enough. We assumed f is C1, and if you look at the equations of characteristic ODE, the right hand side will involve only derivatives of f at maximum, right. Fp, Fq, Pfp plus Pfq minus Fx, Fz and so on, Fy, they are all assumed to be continuous. Therefore, right hand side is continuous the moment you assume f is C1, which means by Pinot's theorem there exists a solution. If you want uniqueness, you push it C2. If you make it f to be C2, uniqueness is guaranteed. So, on solutions of the initial value problem, that is characteristic strip ODE plus an initial strip, we want to solve this initial value problem. So, without loss of generality, we may assume that solutions to the initial value problem, which is given by the ODEs, is a characteristic strip ODE, and the initial conditions are given by the initial strip. They are defined, the solutions are defined for t comma s in j cross I, where j does not depend on s. For quasi-linear equations, it was possible thanks to the lemma on reparameterization of characteristic curves, because the tangential direction does not change under reparameterization. On the other hand, reparameterization of a characteristic strip need not be a characteristic strip. Therefore, this argument does not hold. Luckily, we have another argument. In the case of quasi-linear equations, we had a second argument which we have given, that also allows us to conclude the existence of such an interval j which does not depend on s, but now there is a compromise that the interval I needs to be replaced with a subinterval of y, but that does not matter, because later on what we are going to do is we are going to apply inverse function theorem whose conclusions are anyway local. So, it does not matter. So, what is important is that j does not depend on s, whether it is s belongs to I or s belongs to some subinterval of I. So, the solutions are continuously differentiable functions on j cross I by differentiable dependence of solutions on parameters in the theory of ODEs. In fact, inside the proof of this theorem, one needs to get such catch hold of such an interval which does not depend on s. So, the progress so far has been this: first gamma which is given, then an initial strip we have obtained, that is throughout these points of gamma we have erected these kind of small planes, and then characteristic curves going through points of gamma. If this is the point P, this is the gamma P, small gamma P, and not only characteristic curves, throughout at any point in the characteristic curve we also got this particular normal to some plane. Of course, the plane is expected to be a tangent plane later on. So, for Ts in j cross I, we got f of xts, yts, zts, pts, qts equal to 0, and x0s is fs, y0s is gs, z0s is hs, p is ps, q is qs. So, these are coming from initial conditions. This is the first thing that we did. D by dt f of zeta of t is 0, therefore, f of zeta t is constant, and we chose zeta 0 such that f of zeta 0 is 0, therefore, f of zeta t is 0. So, this is also we have proved in step 2. It followed from the way we chose the initial strip. So, summarizing the steps 1, 2 and the third one, the little bit that we did so far, it gives us the following theorem. Consider the Cauchy problem for general nonlinear equation with Cauchy data. Assumptions: f is C2. Let S be an integral surface for this general nonlinear equation where u is a C2 function. Assume that a part of the datum curve lies on the surface S. Assume that FGH are C2 functions which describe the datum curve. Note these are additional assumptions on f and gamma. Standard assumptions on them still apply, namely Fp, Fq cannot simultaneously vanish and so on, and F prime G prime also cannot vanish simultaneously. Now take a point which is on gamma as well as on S, that means that integral surface which is also there in the datum curve, that point. Let P naught Q naught be such that the equations are satisfied. Assume that the Jacobian condition is satisfied at S naught P naught Q naught. P naught Q naught is this, S naught is which we have already fixed, and here the zeta naught stands for this as before. Conclusion: the surface is the union of the supports of the characteristic strips through the points of gamma, of course in a neighborhood of P0. So, this theorem actually generalizes our earlier theorem that we did. Integral surface is a union of characteristic surface curves. Integral surface is a union of characteristic curves. That theorem we proved for quadrilinear equations. This is a generalization of that. Proof is similar to that, same as that. So, key ingredients here are chara strip ODE and PT equal to this and QT equal to this. So, now question is the road ahead is smooth, because last theorem gives us a hope to find an integral surface exactly like the other theorem which gave us hope in quasi-linear equations using the method of characteristics for general nonlinear equation. However, theorem holds only for u in C2 and FGH in C2 of I. We are looking to solve GE for which a C2 solution may not exist. It is unreasonable to expect a C2 solution for a first order PDE to start with. It may happen that you have a C2 solution or C infinity solution, but to start with you do not expect that. And parameterization of the datum curve is C1 is reasonable, but not C2. So, would that be a problem? Answer is no, that will not be a problem. Details on the next slide. Yes, it is true that we used u is C2 of D, FGH is in C2 of I to derive chara strip ODE and initial strip. Now forget all this and start working with chara strip ODE and initial strip. They were used only to derive these two things, right. Pretend that you were given these two and you are asked to work with them. Everything will be fine. We do not need FGH in C2. So, no need to worry, road ahead is indeed smooth. From now onwards assume that the system chara strip ODE is given and an initial strip FSGS, HS, PS, QS consisting of C1 functions on an interval containing S0 is given. Let the functions STS, YTS, ZTS, PTS, QTS solve the initial value problem and initial strip, that will be good enough. Of course, you may not have solutions which are unique, but maybe correspond to each solution you may get one integral surface, who knows that can happen. So, we derived an initial strip using which the system of characteristic strip equations may be solved. Projection of solutions to XYZ space will give you characteristic curves through points of gamma. In a bid to extend method of characteristics to GE, we come across new geometrical entities. So, natural question is, should we still call it method of characteristics or should we call method of characteristic strips? It is okay, that does not matter, just for you to think, ponder about this question. So, we found an initial strip. Step 2 of our program is successfully implemented. In the next lecture we are going to complete the proof of existence and uniqueness of solutions to Cauchy problem for general nonlinear equations. Thank you.